Welcome back, everybody, for another look at another Nobel Prize. This time from 1924 by a Swedish physicist, and we'll get to that in a second. But if you haven't yet gotten the chance, please click subscribe on the channel. It does help us grow, and it really helps us out with the algorithm. But let's get back to the Nobel Prize. In 1924, the prize went to Manne Siegbahn, whose name I'm probably mispronouncing because Swedish pronounce things much differently than we do here in America, and I do apologize for getting it wrong. But he won the prize in 1924 for his discoveries and research in the field of X-ray spectroscopy. Now, what does all that mean in plain, simple terms? So what that means is he measured the X-ray emissions from different atoms in the X-ray band using a device called a spectrometer. Well, again, I'm reusing the same word to define it. So what the heck does that really mean in plain English, right? You might be asking yourself that at this point. So let's figure that out. Spectroscopy is a big fancy science way of saying I measured things across a particular spectrum. And all that spectrum really means is across some range of data. And when we say range, usually in a spectrum, we're talking about wavelengths or energy levels or something like that. But in this particular case, we're talking about wavelengths. So what you see here is not an X-ray spectra. This is of any large atom. This is a optical spectrum of deuterium, which is one of the hydrogen isotopes. And when you see those peaks are very characteristic. The ones labeled with the D are very characteristic of what you see coming out of plutonium. When you get plutonium excited, and we discussed in other videos about how when you get things excited and those electrons go up to higher levels, then they cascade back down to their ground state, it comes with emission of some light of some wavelength. Well, in deuterium, you get what you see here. With other atoms, you get other things. And as you get to larger and larger atoms, and you deal with those inner shell electrons, because remember, electrons come in different shells. They have ones that are closer in, and they have electrons that are further away, that are less tightly bound. But as you get those really close in ones really excited and they cascade back down, you will find things will actually emit in the X-ray region as well. There was a Nobel Prize awarded for that early on. And you can go back and watch that video as well. But what he did was he dug really deeply into the X-ray spectroscopy of a lot of different elements, and he uncovered a lot and told us a lot about the modern day understanding of the electron shell, which at the time was still not completely understood. So now let's look at that. What the heck is an electron shell? Well, what you see here is an AI generated image of a helium atom. You don't normally have these little splotchy things in the background. That's just an AI artifact, but I thought it was cute. So the electron shell is really thought of as the orbit of electrons around the atom's nucleus. The closest shell in is called the 1 shell, sometimes it's called the K shell. The next one out is the 2 shell or the L shell, and then they kind of go further and further away. So the closer in you get, the fewer electrons they hold. So as you get to larger atoms, there's a lot more electron shells. You can have, it goes pretty far out depending on how big the atom is. But in the first electron shell, what you have is 2, that's what you see here. It's helium. As you go further out, they get to be larger and larger. Now, as you excite electrons, they're going to be further away from the nucleus. And that electron shell and how they cascade back down and go from like a 4 state to a 2 state or a 3 state to a 1 state, that gives you the different emissions that you see on the atomic spectra, or the visible spectra, the X-ray spectra, the UV spectra, wherever you happen to be looking and wherever is appropriate for that particular atom. But what these orbits do is they help you kind of work it backwards and say, okay, now that we know these orbital states are quantized, they can only be, you can't have something orbiting in a 1.5, spot. You can only have them in integer multiples, at least as far as we're aware so far. But that electron shell, the shell tells you where inside that electron cloud that they are. Not all electrons are as close to the nucleus as all the others. They have different orbits. And those orbits collectively make up what's called the electron shell. And the more we know about that, the more we can do proper chemistry and understanding of what the different atoms' capabilities are as far as bonding and having stronger bonds versus weaker bonds. And it really does lay the stage for a whole lot of chemistry that came in the 20th century. Now, after winning the Nobel Prize, he wasn't finished. He didn't just go, thank you for the prize, and retire. No, he went on to do a lot of other things. What you see here is the California Berkeley 60-inch cyclotron as it was built in 1939. Now, these are huge devices. I used to work in a lab that had one in it. They are massive, very difficult, if not impossible to move. You kind of build them and build a building around them. kind of devices. They're massive. So they're used for a lot of different research purposes, and they're huge, and you see the people in there for scale. But in 1937, our Nobel laureate this time out became the director of the Nobel Institute for Experimental Physics in Stockholm. That particular institute became pretty much the leader in Swedish cyclotron research. And he also developed this extensive international network of researchers that were kind of all focused on the same areas that he was on, because it was very exciting stuff. It still is very exciting stuff. And in fact, one of his two sons, by the name of Kai, followed in his footsteps and held that very same chair, and by the way, also won the Nobel Prize in 1981, which we'll get to that in a later video. I hope you've enjoyed this. This particular Nobel Prize winner is not really all that well known, but given what he taught us about the electron shell and how much that influences a lot of modern day chemistry, I think he deserves a little more attention than he typically gets. So everybody have a great day, and if you haven't yet, please click that subscribe button and click like. It really does help us out with the YouTube algorithms, and have a great day.